It is a pleasure to welcome you to the third edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The International Workshop on Unsaturated Soils was hosted in 2022 during the third edition of the AGERP lecture series. The following lecture on plant soil interaction effects on the hydromechanical behavior of unsaturated slopes was delivered by Dr. Vittoria Capobianco at this workshop. Vittoria Capobianco received her PhD in Geotechnical Engineering at University of Salerno, Italy, in 2018 on the effects of roots on the hydromechanical behavior of unsaturated pyroclastic soils, where she carried out an experimental study at lab scale. Part of her PhD research was conducted at Hong Kong University of Science and Technology, where she improved her knowledge on soil bioengineering techniques and conducted an experimental study on the effect of nutrients in soil on plant growth and the induced soil hydraulic response. Her main research topics are root-soil interaction in unsaturated slopes and soil water bioengineering as mitigation measure for rainfall-induced shallow landslides. The results of her research are published in several international journals and national and international conferences. She is project engineer at the Norwegian Geotechnical Institute, where her main activities are related to applied research on EU and national research projects related to nature-based solutions for natural hazards mitigation, as well as geotechnical consulting projects. Since 2021, she is the convener of the session entitled Vegetation as Nature-Based Solution for Mitigating Hydrometeorological Geohazards on Slopes and Streambanks at the annual conference of the European Geoscience Union. She will be the chair of the third workshop organized by the Joint Technical Committee on Natural Slopes and Landslides on Impact of Global Changes on Landslide Hazard and Risk, to be held on the 7th-10th of June 2023 in Oslo, Norway.
Good morning or good afternoon to everyone. First of all, I wish to thank Partha and the organizing committee of the AGERP for inviting me to this third edition of the International Workshop on Unsaturated Soils. As Partha already introduced, my talk today will be about plant-soil interaction effects on the hydromechanical behavior of unsaturated soils and slopes. And it's a pleasure for me to share some of the research that I've been doing both at NGI and previously at University of Salerno in Italy, where I took my PhD. So here are the main topics I will touch upon during, let's see if I can also put the laser pointer. Okay. Here are the main topics I will touch upon during this talk, starting from the motivation. We as geotechnical engineers want to study the effect of plants in the unsaturated zones. Then we look more into the root-soil interactions and how roots and soil can mutually affect each other in multiple ways. Later, I will talk about the scales of study and application, and more in detail, we'll talk about vegetation as and its effects along a slope and how to quantify them. So we will briefly touch upon the hydrological reinforcement, the mechanical reinforcement, and other types of reinforcement that vegetation may have on soils. And finally, we can see how also how external factors can influence the roots growth and how this affects also the soil properties to our advantage. In conclusion, we can have some discussion, some conclusions, and takeaway messages. So first of all, we have all seen that recently a strong attention is put from the geotechnical engineering community on exploiting vegetation as a live material for sustainable engineered practices. We may go from bioengineered slope to landfill slopes, etc. And all these have been called in different terms lately, from nature-based solutions to soil bioengineering, bio-inspired solutions, plant-based solutions. And for slope stability problem, we mostly refer to the use of vegetation for reinforcing the shallowest layers of a slope. These approaches, though, require a deep understanding of the so-called plant-soil atmosphere interaction. Attempts have been done to summarize all the potential effects that vegetation and its parts, including roots, can have on the soil physical, chemical, mechanical, and hydrological properties and hydraulic properties. And this is a schematization that shows how it is not only the roots that affect the soil properties, but it's a mutual interaction that goes on both directions. For example, also soil can affect the root features, such as root diameter, number, type, but also the root structure, the tortuosity, the root architecture, and consequently also their mechanical behavior. On the other hand, what interests us as geotechnical engineers is how roots are actually affecting the soil properties. And we know that roots can affect soils by changing its physical properties from particle size distribution, pore size and tortuosity, bulk density, but also mechanical properties, for chemical properties such as mineral composition, presence of organic matter, or microorganisms present into the soil. Regarding mechanical properties, it's well recognized that roots are increasing the stress path in the soil, as well as the apparent cohesion, or in some cases also the integrated friction angle. And this all depends on the number of roots and the type of roots that are affecting the soil. From an hydrological point of view, plants can interact with the soil and especially with the water present in the soil for exerting their vital function through photosynthesis or through transpiration. And this consequently changes the soil suction and water content and the hydraulic conductivity. So with today's talk, I will mostly focus on the effects of roots on physical, mechanical, and hydraulic properties of soil, and touch briefly upon the root features and root structures. The composite root soil material is a complex system formed by 4 phases. We know that it's water, air, soil, and roots. And these latter are also alive, thus cannot be treated as traditional constructional material. And to simplify such a complex problem, we tend to isolate the effect of roots and try to study them at the single root level first. At laboratory, for example, this allows us to model the behavior of the single root to try to find some laws. And when considering, for example, roots at bundle level, we can try to do some measurements and find patterns that can explain such behaviors. However, in real-world problems, the situation is more complex, and at the slope scale, it's not possible to isolate the effect of a single root or a root bundle, but we need to take into account the whole effect that roots can have to each other and to adjacent vegetation. So the current research on this topic is mostly on understanding first the behavior of root-permeated soil by quantifying the effects on soil properties, especially at lab scale when we have a controlled situation, we have something that we can control, we can isolate different effects in order then in future to be able to design proper plant-based solutions for real-world shallow instability problems. And this schematization shows all different types of effects that interest us as geotechnical engineers when it comes to assessing the role of vegetation in slope stability. So we may group this effect in 3 main effects, as I said earlier: hydrological effects, mechanical, and other effects. So we all know that above ground vegetation, for example, affects the change in surface water runoff or rainfall interception, as well as evapotranspiration. Roots can instead have both effect on the soil mechanical properties, but also on the hydrological part. For example, they may change the infiltration rate, but they can also change the soil water content through root water uptake, thus also changing the level of the phreatic line. On the other hand, we know that roots can improve the shear strength by additional cohesion and act as anchors with a pull-out resistance as well. Other effects can be additional surcharge, for example, the load of the weight of the single tree, which actually has been demonstrated that it's not as important as other factors, so it can also be neglected. But other effects can also be change in physical properties that in turn may influence also the hydromechanical properties of the root soil composite. The modeling of vegetated slopes implies that all the effects that both roots and above ground vegetation are taken into account, directly or indirectly. And this is a methodological approach that we adopted for slope stability. We can adopt for slope stability modeling of a vegetated slope. You can see that here we have as input data, we give normally the slope geometry and the soil properties, which for soil permeated roots, for root permeated soils may change. For example, we could assign a slightly changed hydraulic conductivity on soil given by the presence of roots. And this can be, for example, measured first in laboratory and then put into the model or taken from literature. The same is also for the changing bulk density or the changing porosity, so the soil structure, how it's changed due to the presence of roots. And also the soil mechanical properties. For example, the easiest way to take into account the roots is to add an additional cohesion due to the presence of roots. On the other hand, processes influenced by the presence of vegetation are the water balance. So whenever we have to do a slope stability modeling, we do the hydrological modeling to assess the pore water pressure regime with this seepage analysis. And then we apply, for example, liquid equilibrium method, and we calculate the safety factor. In the hydrological modeling, what we do is to make a water balance, basically. And into the water balance, the canopy area, so the above ground vegetation, has its main role. And this is exerted by the evapotranspiration, which is influenced by the leaves. But also the interception and the infiltration may be influenced by this. So once considered all these factors, we may perform a slope stability modeling and calculate the safety factor of the vegetated slopes. And let's see these effects and isolated first and how to quantify them separately. Starting from the hydrological reinforcement, this is probably the most complex to study because it depends on many factors and it really affects the unsaturated root zone. In the image here, you can see the so-called soil, plant, air continuum. And to exert their vital function, the plants, what they do is to let the water flow from the soil through the roots and through the stems up to the air. This is called transpiration, and there is no interruption of this flow of water into the plant that can be said that the plant is the medium through which the water moves. And the water is moved through a difference in water potential generated by the leaves on top, and then it flows upwards from the roots up to the atmosphere. As I say, this process is known in botany as a transpiration. What is interesting for us is to understand how this process is actually affecting the unsaturated root zone. So everything that is in the vadose zone where roots are actually affecting the presence of water. And we know that the process of transpiration generates a reduction in water content in the soil and consequently an increase in suction. And this increase in suction increases the shear strength due to apparent cohesion and binding forces. Some studies have also shown a clear correlation between the increment of matrix suction due to root water uptake and the increment in penetration resistance into root permeated soils. If we take the extended Moore Coulomb failure envelope for unsaturated soil, and we translate it for a case of an unsaturated rooted soil composite, we have a clear factor that increases the overall shear strength, which is the induced suction due to water uptake. However, This hydrological reinforcement may not be constant with time, but it can change and can be affected by seasons, especially in temperate climates, for example, in Europe. It's been demonstrated that there is a quite strong seasonal dependency of the change of hydrological reinforcement due to the presence of roots. And this has been demonstrated recently by Baldwin et al. In 2021, which shows how seasons affect the induced suction into the soil and consequently the shear strength. Here you see that in summer, indeed, we may experience some suction peaks that are given both by the pronounced evapotranspiration and transpiration, mostly given by an increase of temperature and increase of the amount of water actually needed by plants to survive during drying periods. So to suction peaks, we actually may also see that corresponds strength peaks. And this is done in situ, where we see also how the strength peaks are measured. On the contrary, some studies, including this one, have actually showed that the actual hydrological reinforcement given by plants in the autumn season or in the wet season can be almost neglected. So we can have two different order of magnitude of this effect going from summer to autumn. And this seasonal effect is confirmed also when modeling the evapotranspiration along a slope. Here we have a slope which actually in site is vegetated, and it's located in central Norway with, you see a firm marine clay layer here at the bottom, which is in saturated condition. And then we have on the top this layer of about 6 meters of sandy silt in unsaturated condition. We have been monitoring this slope since 2016. And then we performed a modeling using the commercial software GeoStudio. And the different series that we modeled were 3. By changing the surface hydraulic conditions. One was only considering the actual rainfall registered from a nearby weather station. The second scenario was considering also evaporation, including climate drivers such as air temperature, wind speed, and relative humidity. And the last series was considering both the climate drivers and the presence of vegetation. And these effects are taken into account by calculating the evapotranspiration value through the Penman-Montet equation applied at as a boundary condition. What we observed in a period of 6 months of simulation from June to December is that when comparing the safety factor calculated for the 3 different scenarios, we may have actually quite significant change in the safety factor calculated. So when we consider, for example, only the rainfall as boundary condition, is always calculating a safety factor below 1, which is actually underestimating the real situation, since the slope is under monitoring and it's still stable so far. But when we consider also the climate boundaries acting in the unsaturated zone, we have seen an increment of the calculated safety factor, which is even higher when we consider also the presence of the vegetation. So by looking at these differences, we can say that we have a difference of about from 11 to 18% of difference between the non-vegetated and the vegetated. And we have about 0 to 6% of difference between the scenario 2 only with climate drivers and the scenario 3 including vegetation. And as we say, seasons are also affecting this change in safety factor with time. It's possible to observe that here in the summer months, from let's say March to September, June to September, July to September, we have an increasing trend of the safety factor, which can then decrease when the autumn season and the winter season are approaching. Not only the seasons may affect the hydraulic behavior of soil, also the roots growing with time, so the aging of roots. And roots growth affects the hydrological reinforcement, and that's been demonstrating in this lab experiment conducted at the University of Salerno, where we had these two long columns of 2 meters height. One was left bare as control, and the other one was vegetated with grass, long root grass that can develop up to 2 meters roots. Tensiometers and soil moisture sensors were placed at different depths along the column to monitor the soil hydraulic behavior under drying and wetting tests during the roots growth. And here we have also monitored the root depth and the length of the leaves with time to see how the roots were developing in the first vegetative year. The monitoring lasted 2 years, and during the roots growth, we performed several drying and wetting cycles. The drying cycles consisted in starting from a saturated condition of the column and then leave the column to dry for 15 days under atmospheric conditions. And this was done in 2 different periods of the year. The wet season, which is like the spring season in Italy, and the dry season, which is in summertime. And also wetting tests were applied through artificial rainfall for 48 hours, starting from different initial suction conditions and different rainfall intensity. This is a representative image of what happens into the rooted soil as the roots develop. We weren't able to take only one trend curve of suction and degree of saturation, but we took 3 different curves for 3 different periods of the monitoring. The first ones are at 4 different depths compared with the dashed line, which is for controlled soil. And it's at the beginning of the season, so when we first planted the grasses. The second one is during the middle, so during the roots growth, but not when they were completely developed. And the third one is when the roots were already well grown. So the tendency to flatten is visible, particularly for suction higher than 10 kPa, while after that value, the roots probably increase the water uptake collected into the capillary tubes. And at the end of roots growth, the curves of the vegetated column are flattened at all depths and show higher values of saturation degree compared with the bare reference curves. This means that for the same suction, the saturation degrees increase from 1 month to the next. And one possible explanation of this is that roots during growth can develop and occupy parts of the voids, thus modifying the global porosity of the host soil. This means that the rooted soil has a higher retention capacity, and also that when we consider the effect of roots on the hydraulic properties, for example, soil water retention properties, we need to consider a dynamic change. So it's not only a spatial change, because we know that with depth, the soil water retention curve may change, but it's also a time-dependent change of the soil water retention capacity. So let's move on to the next reinforcement, which is the mechanical reinforcement. It's pretty straightforward to conclude that roots are improving the shear resistance when intercepting a shear failure. This mechanical contribution, though, is exclusively exercised in the rooted zone, which in 75% of the cases is within the first 40 centimeters of the soil. Therefore, if we zoom into the slope, the three highlighted actually is contributing with these roots only to the resistance of the first 2 sliding surfaces. And this resistance is decreasing with depth, because as depth increases, the root density decreases. And this mechanical reinforcement along the shear surface is considered as an additional cohesion. So in unsaturated condition, we have another factor now that is affecting the shear strength of the soil. So in the recent years, there have been a lot of attempts to model the effect of of roots on the shear strength. And the first attempt was done in the 70s from Wu et al. With the W&W model, which calculates the root cohesion as a function of the tensile strength of the root and tangential stresses and normal stresses that are created along a shear plane. So basically, these stresses that are created along a shear plane are explained as a function of the tensile strength by means of a certain distortion angle. And since it's difficult to consider this distortion angle, we normally consider a factor K1, which is normally equal to 1 or 1.2. However, this type of model has demonstrated to overestimate a little bit the radical reinforcement. But if we look more in detail at the tension, the tensile strength of roots, this is given by the sum of the tensile strength of the single roots that intersect the failure plane that belongs to a specific diameter class, multiplied by the root area ratio, which represents the surface occupied by the roots per soil unit. So here you see a schematization of the root area ratio, which decreases with depth because the root density is naturally decreasing with depth. And here at the bottom right of the picture, you can see there is a collection of tensile resistance of different plant species from the Mediterranean area, taken from literature. And you see normally the root tensile strength is function of different root features, but most importantly is function of the root diameter. And here we see that as the root diameter increases, the tensile strength tends to decrease. Many experiments have been done to define this tensile strength, and it can be easily obtained in lab with a tensile test, which is similar to the ones that we make for determining the tensile strength of steel reinforcement bars for concrete structures. I won't go in detail about all the other types of methods that can be used for evaluating the root reinforcement in shallow landslides, but I give you here a reference that can be very comprehensive, and it collects all this type of methods for reinforcement of shallow landslides given by roots. But going back on how to quantify this at lab level, what has been done so far is to perform direct shear tests for assessing the roots reinforcement. And this has been done during the last decades at lab scale, but also at site scale. From the direct shear test, we are able to obtain the failure criterion and assess the additional cohesion exerted by the root system. Here you see the one for bare soil, and then how this failure envelope is translating up depending on the type of species that have been tested. And this way is possible to calculate the additional cohesion. In this other example, we see that we have a representative shear versus the displacement of rooted soils, which are these three curves, and bare soil, which is this one more in black. We can observe not only an increment in the shear stress that is tolerated by the rooted soil, but also a dramatical increment of the maximum displacement allowed in the rooted zone. And these are three curves for three different depths of the shear surface applied in direct shear tests. One of the advantages of direct shear apparatus is that it allows to reach high deformation that mobilize roots, while the limitations are related to a predetermined shear surface, and also that horizontal stresses are unknown. Indeed, few triaxial tests have been conducted also on rooted soil composite samples in recent years, and some of them are involving a change in root geometry and root distribution in a way to better simulate the natural root distribution that we could find on site. On the contrary of direct shear tests, triaxial tests can be performed in different drainage conditions, and the failure surface is generated along the weakest surface. Some of these studies have also found that roots, especially grass roots, can also lead to a slight increase of the friction angle. And in this research, which is the same we conducted looking at the hydraulic properties of soil, at the end of the drying and wetting cycles, we took samples at different depths of the columns in order to assess also how the presence of root may have changed the rheology of the soil and thus the behavior under failure. The type of soil we studied was this loose pyroclastic soil, which is prone to rainfall-induced landslides. And the mechanism that normally brings to the failure is in consolidated undrained conditions, when it may undergo to static liquefaction when pore water pressure are not dissipated. So what we did was to take different samples at different depths, and then we also calculated some of the main root features, such as diameter, root mass, and root volume density. And here you can see that again there is this distribution which decreases with depth. If we look at the results for different samples with different root volume density, compared with the bare samples, which are those with the red continuous line, in consolidated drain tests, both the bare and the vegetated soil specimens with initial void ratio and root volume density showed a contractive behavior provided by an increase in the volumetric deformation and as the axial strain increased. Many rooted specimens, though, showed an hardening behavior, being globally flattened as the consolidation pressure increased. Results showed also that specimens showed an increase in shear strength over the non-rooted samples. So we're talking about an increase in shear strength of the vegetated ones over the non-rooted ones. And also that we have an increased stiffness. Indeed, in the elastic phase of shearing, the axial deformation recorded in the vegetated samples under the same deviator stresses were generally lower than the one recorded in the bare samples. So this presence of roots can generally increase also the stiffness of the composite root soil system. When we look at the undrained test results, this is only for 30 kPa of consolidation pressure. So let's zoom on this one. And for the bare soil, upon shearing, we observe a drastic increment of the pore water pressure, leading to a reduction of the mean effective stress as the deformation increased. In some cases, the mean effective stress, here you can see for the bare soil, actually dropped to zero, which is the typical behavior of loose pyroclastic soils involved in the static liquefaction process. So actually, we observed that complete static liquefaction occurred only for the bare sample. If we look at the vegetated samples instead, with different root volume density, as the root volume density increases, we see an increment of the maximum deviator stress, as well as a reduction in the excess pore water pressure that was observed. And the specimen with the highest root volume, which is this dashed black line, showed a stable behavior, even with tendency as a dilative-like behavior. You see that the deviator stress increases as the strain increases. And it's confirmed also by a small increment of the pore water pressure as long as failure is approached. So these final shapes of the specimens also are significantly different. Even if they both experience a diffuse failure deformation mode without the formation of the defined failure plane, the bare one liquefied while the vegetated specimen did not, because of the light root network created within the porous space. If we look at the failure envelopes, and we compare the bare specimen, which is the one with the orange triangles, vegetated specimens showed again an increase in root cohesion, which translates the failure envelope upwards, and despite relatively small, also an increase of friction angle. In this case, the integrated friction angle is then also affected, and a stress-dependent contribution of the roots on the shear resistance can be proven. Here we see a variation of root cohesion in the range of from 0 to 5 kPa, and this cohesion increases as the root volume density increases, while for the friction angle we saw just an increase from 0 to 3 degrees. And assuming friction angle to be unchanged by roots is not always true, and this has been also demonstrated by other studies conducted by Leung et al. Recently. Let's look at other reinforcement. An example of other reinforcement, other than hydrological or mechanical, is given by the change in physical properties, such as porosity or structure. When roots develop, they can also act as compaction to the soil aggregation. This increases the bulk density and reduce the soil porosity. In loose soils, in unsaturated conditions, this may lead also to a reduction of collapsibility of the root soil composite. On the right-hand side, we see how Charleston has proposed a new volumetric phase diagram of a root permeated soil, where actually we have an extra phase, which is a solid phase, which is the root component. And here is an example of effect of roots on the collapsibility behavior of this pyroclastic loose soil, which have shown a collapsible behavior upon wetting. So the experimental setups consist in 4 cylinders filled with moist stamping method with pyroclastic soils at 4 different initial porosities. Then after that, we put on the surface some seeds, and then we waited until the seeds were germinated, and we left for a growth period of 20 weeks by watering the surface only by spraying some water on the top. During the plant growth, as we can see from this graph, the soil level was measured with a scale put on the side of the plexiglass columns for 3 different stages. Initial condition, after 10 weeks of roots growth, and after 20 weeks. And we were able to compute the variation of the void ratio during the roots growth, and we observed that the initial porosity was progressively reduced compared to the initial soil condition in all cylinders. And the decreasing trend observed may be due to several factors, such as that roots occupy pores and enhance the soil aggregation. They produce exudates. So these exudates are actually also enhancing this root aggregation, or they dense and they create this clustered root network that facilitates a reduction in the soil porosity through links between soil particles. But let's look at the experiments that we did. After 20 weeks, we extruded some samples at 3 different depths, 30 millimeters, 80, and 120 millimeters. And we took some edometer samples of vegetated soil. And then we compared them also with the bare soils. After each edometer test, we have also measured root features in terms of root mass density and root volume density. And what we observed from this graph is that here we have a correlation between the initial void ratio, so the design void ratio of the cylinders, and the root volume density for the rooted specimens taken at the 3 different sampling depths. It's clear that roots are able to grow better within a more porous initial soil structure, and also that their volume decreases with depth, because here it's 30 millimeter and it's the highest volume, and then it starts to decrease with depth. Finally, we did this edometer tests under 13 kPa of consolidation pressure, starting from the same saturation degree, and then we basically flooded with distilled water the edometers and calculated measured the displacement after the collapse for each test. And calculated afterwards the coefficient of collapsibility due to wetting according to this formula. Then we compared the results of the vegetated specimens with the ones that we did previously on the bare soil. What we observed was that if we put the collapsibility, the coefficient of collapsibility with the initial void ratio in this graph, we observed that while the trend of collapsibility for bare specimens increased with the initial void ratio, meaning that as the void ratio is higher, also the collapsibility is higher, the collapsibility expected is higher. With vegetated soil, we were already starting with a very low initial void ratio because of roots growth compared to the bare soil. However, for similar initial void ratio, we can see that in this range, for example, we see that the coefficient of collapsibility is further reduced in rooted soil. So actually roots are also reducing the collapsibility behavior of unsaturated pyroclastic soils. Let's look at the end at the external factors. The mutual influence of root and soil can be affected also by external factors. And here, for example, you see the root distribution, two root systems. The first one is only with a simple one-order lateral root. So we have the main root system, and then we have just order lateral roots coming on the sides. On the other hand, we have a more complex root system because we see that we have a proliferation of roots of second and third lateral roots that are coming from the first order lateral roots. And this is something that we know we can actually observe, for example, when we have a good availability of nutrients into the soil. So when there is a good presence of nitrogen, phosphorus, or potassium, which are those that are actually helping the plants to grow better and are needed by the plants for exerting their vital function, we can also observe a change in the root structure, which eventually may change also the soil hydromechanical properties. How can we reach this nutrient availability? It's, for example, by adding some fertilizers, as we do for our plants at home as well. So in this research, in collaboration with the HKUST, we tested the influence of fertilizers on roots development in compacted soil for man-made slopes in Hong Kong, and how this actually may affect the hydraulic behavior of soil. So we tested 3 series with bare soil, the first one as control, which was left without vegetation. And then we had 2 series of vegetated soil. One was left as control without adding nutrients, and the other one was by adding an NPK liquid solution, which is nitrogen, phosphorus, and potassium, to a ratio 30-10-10. And this was done for a period of 6 months by supplying every week water and nutrients for the nutrient series. Here you can see some details of the experimental setup. So there were these columns where we also added soil moisture sensors and tensiometers to monitor and to measure the change in soil suction and water content in the rooted area. After 6 months, we observed that nutrient-rich soil had actually allowed a denser root system development, as well as a higher leaf area index. So as you can easily see from the pictures, it's pretty obvious that the root system that developed in the nutrient-rich soil is more complex, it's denser, is more healthy. The same is for the leaves, where here is an example of leaves grown in a nutrient-rich soil, and here is just with soil, with water. And we've also measured the change in root area index and in leaf area index. And you can see that the blue lines are those that correspond to the nutrient-rich soil, which are higher both in the two cases. This, of course, is reflected also into the soil hydraulic properties. And it's reflected in a significantly increase of the induced suction during evapotranspiration. Again, here, as the root density increases by nutrient supply, we see an increment in induced suction. And here is done at different depths and for different days. So this is for 3 days after complete saturation, 3 days of drying. So we don't see a big difference between the three series. But after 6 days of drying, we can actually see how the nutrient-rich soil had a much higher induced suction because of the roots presence that was much more complex and much more denser, which helped with the induced suction. So we may say that by controlling some soil conditions, we may achieve a better root development and thus a better response also in the soil hydraulic behavior. So this can be used at our advantage, because whenever we are going to use plants and to design vegetation-based solutions with assessing these different effects that vegetation can have on soil, we may also decide to artificially change also somehow the root features at our advantage in order to get and to gain a better performance also in the unsaturated zone for the slope stability. I finished by adding 3 main points, basically 3 takeaway messages from this talk. We have seen, first of all, that plants have multiple effects on slope stability of unsaturated soils. And we've seen that at laboratory scale, which is the first step towards understanding a real world problem, we can actually study each effect isolated and try to find patterns or try to find trends that can be transferred to real world problems. The second point is that each of these effects are not constant, but they can vary. They can be time and space dependent, and they depend on the mutual interaction between plants and soil and external factors, such as atmosphere or addition of nutrients, etc. And these are, for example, the seasonality we have seen the roots growth may change also and may affect the hydraulic properties. The initial soil porosity may affect the roots growth and consequently also the collapsible behavior of rooted soil, and the nutrient availability may affect also the soil behavior. So the last takeaway message from this is that we are dealing with a very complex problem, and as engineers, our role is to simplify a complex problem. But this is not only a complex problem, it's also a multidisciplinary problem. So it requires a cross-sectional collaboration between biologists, ecologists, engineers. So not only engineers can deal with this problem, because we are dealing with the live materials that have their own characteristics, they have their needs, they have their factors depending on climate, and etc. And the help of external skills that are not competing with our engineering skills may actually help us in identifying a solution to this problem. So there is still a long way ahead. We are in the phase of still understanding what are these patterns and whether we can find some standards in future to be able to use vegetation as a means for stabilizing slopes. But it's so it's still everything ongoing, a work in progress. And I hope that this talk was able to clarify some of the main aspects that are actually interesting the geotechnical community for assessing the effect of vegetation on unsaturated slopes. Last, I leave you with this slide, as Patra also introduced. Before jumping to the Q&A session, I take the opportunity to promote the JTC1 workshop on impact of global changes on landslide hazard and risk. The workshop is being organized by NGI with the support of the Joint Technical Committee on Natural Slopes and Landslides and the Federation of International Geoengineering Society. The workshop will be held physically in Oslo in June next year, but here we are calling now for abstracts. Deadline for abstract submission is June this year, so it's in 1 month. So I can tell you that these are the main topics we will deal with. And the one topic also is related to landslide hazard, but also including risk mitigation strategy, as well as nature-based solutions. So in contributions using vegetation to stabilize unsaturated slopes are very welcome. So please do not hesitate to either look at the website or just contact me in case you have any doubts or you are willing to submit a contribution. And I hope to see some of you in Oslo next year. And then I guess we can jump to the Q&A session. I hope I stayed in time, and yeah, that's all. Thank you. I mean, not specifically in the results fair, I may say. What we did was to put it at different depths of the soil, but not specifically in the results fair. So that I don't know. I think it's something that we should look at. There are probably some studies that have done that, and this for sure may also influence the mechanical and hydromechanical behavior of soil. So it's definitely something to look at. Yes, very interesting question. It's a good question. I think I quickly touched upon this when I talked about the different effects that vegetation can have on slope stability. And there are different opinions about this in the community. Definitely, depending on the type of species you have, you may have an extra load or not that affect the slope stability. So as you pointed out, if you have woody plants like trees, big trees, those are definitely affected also by the wind, and the wind can change also the load effect on the vegetation, on the slope stability. If we are talking as non-woody plants of grass or shrubs, this type of load is really neglected, so it can also be not considered at all. But definitely wind speed is a factor that affects the load for woody plants. Yes. So that's a really practical and good question, I may say. And what it's done so far is to, whenever you do, you design soil bioengineering solution for an embankment, when using vegetation, you do first the stability, considering only the effect of soil, only the shear strength of soil, because you are actually considering that roots are not developed yet. And then you consider a second scenario in the long term, when actually roots are developed. This long term may change, may change depending on the type of species, because it can be that after 2 years you have a complete development of roots, but it may also be that in 5 years these roots are already decaying, and this decay of roots may also reduce the shear strength. So it's really, but normally what it's done in the design is that you do a first stabilization, a first calculation only including the soil shear strength that you pointed out, and then you do a second calculation in the long term and looking at the long-term effect. Yes, so that's how it's done in the conventional and traditional engineering practice.
Yeah, thank
you. That's another good point. Actually, it's been also studied the effect of earthworms on the change of soil behavior. This was beyond the scope of my research, so I didn't really look at the presence of this these engineers of soils. But there are some studies looking at this, so I highly recommend you to look at this in literature. Definitely, the presence of these microorganisms or whatever is also affecting the soil behavior. But as I told you, like, it's difficult to consider all these effects. Normally what we do is just to isolate on one effect. We concentrate on one effect and try to find some patterns. But of course, those patterns can also be affected by other types of effects coming into it. But I haven't looked at this closely.